All right. So, good afternoon, everybody. Welcome to this session with only one lecture this afternoon, given by Cecile Repellin from LPMMC CNRS Grenoble. So, Cecile will tell us about strongly correlated 2D quantum systems, and with an emphasis, of course, on numerical approach, numerical signatures of topological order. So, Cecile, you have an hour and a half. We are pretty flexible, of course. So if there are some questions, we will tell you either from the chat or from a raised hand. And that's it. So please, thank you.
Okay, thanks, Nicolas. So hi, everyone. So today I'd like to tell you a little bit about some methods to probe topological order in strongly correlated 2D systems. So the goal of this lecture is going to be to see some numerical signatures of topological order and more specifically the functional quantum Hall effect and related phases using exact diagonalization or DMRG. So it's going to be a lecture that's really not so much centered on algorithms and on how to technically do these things, but more once you've understood how these tools work, how can you extract some physics from it? How can you read finite size data and extract some universal signature from that? So, so the physics that I will be talking about during the lecture is the physics of topological order. Yes, so I forgot to say, of course, really don't hesitate to interrupt me with questions either from the chat or, well, also by unmuting yourself. And later on, you can also ask questions in the Slack channel and I'll do my best to answer them. Yes, so the physics of topological order. So we're talking about two-dimensional incompressible quantum phases. So, so they will be they have a gap in the bulk, and those are phases whose charge excitations are anyons. They're neither bosons nor fermions, which is allowed by the fact that you are in 2D, so that those two paths, those two ways of moving one particle close to another one are not equivalent. So you have two main possibilities. You have abelian anyons, where when you exchange the two anyons, you will acquire a phase, which is just a scalar number, a complex number. Or you have non-abelian anyons, where it's not enough to specify the position of all the anyons in the system to fully specify the quantum state. You have this degeneracy with two represented by two wave functions, psi1, psi2, and doing an exchange operation in your system of anyons will do a rotation in this degenerate manifold. So a system with topological order is a form of topological insulator in the sense that there's no local order parameter that you can measure that will tell you what this phase is. But it's also distinct from what we typically call topological insulator in the sense that it's not a topological band. So it relies on strong interactions. And one way to think about it is in terms of entanglement. There's no way to, if you have a state with topological order, there's no way to write it down as a product state in any single particle basis, which you could do if you had a topological band by just working in the I don't know, for a full band, for example, you can write down a Slater determinant of Bloch states. So let's see a few examples. So probably some of you are familiar with the toric code, which is a two-dimensional model of spins on a square lattice with some star and plaquette operators. And this model realizes a so-called Z2 topological order. So it's a type of topological order that preserves time reversal symmetry. Another example, which is maybe more physical, or at least observed in the context of solid state system, which is the fractional quantum Hall effect, obtained when you have a large magnetic field in 2D and where you can see a quantization of the whole conductivity. So in this case, you have a breaking of time reversal symmetry. It's in any case explicitly broken by the magnetic field. And an example is, for example, the 1/3 Locken state, which was the first observed fraction in the fractional quantum Hall effect. It has a whole conductivity of 1/3 times E squared over H. And the anyons in this case have a charge E/3 and an exchange statistics theta equals to 2 pi over 3. And finally, just to give an example of how varied this notion is, you can encounter topological order in quantum spin liquids also in principle, in spin systems that have so much frustration that there's no symmetry breaking even at 0 temperature. And in this context, you could in principle encounter both states that have preserved time reversal symmetry, such as Z2 spin liquids, which is in the same universality class as the Turing code. Or you could also encounter chiral spin liquids, which are in the same universality class as the fractional quantum Hall effect. So for the purpose of this lecture, I will be focusing on the category in the middle, the fractional quantum Hall effect. And why is it important to have numerical tools to approach these topologically ordered phases? Well, as you may know, in the case of the toric code model is an exactly solvable model, but really it's an exception. It's extremely convenient to study properties of anyons, for example. But if you want to look at a more realistic Hamiltonian, then you are going to need numerics in order to, well, first of all, know what is the nature of the ground state. Is it a ground state with topological order or not? So this is the purpose of this lecture, to understand how to extract those properties from numerics, know what is the nature of the ground states from numerical data. We have strong correlation, so it's a hard problem, but actually we are not in it could be worse in a sense if you think of strongly correlated matter in general, because topological order phases have a gap in their bulk, or if you prefer, finite correlation lengths. And this tends to be quite good for numerics. This provides a good finite size convergence because it's sometimes possible to reach system sizes that are a few times larger than the correlation lengths. And within the GMRG context, you know that what's very important is to have an entanglement entropy that doesn't grow too fast. And because we are in the case of a gapped phase, there is an area law. So it doesn't grow as widely as a volume law in this case. So here is the outline of the talk. So I'll first start with some elements of fractional quantum Hall physics and of their lattice realizations as well. So just a little bit of physics background on these fractional quantum Hall phases. Then I'll move on to their numerical signatures from first from exact generalization and then from GMRG. And then if we have enough time and if there is enough interest for this, I will also talk about experimental signatures. The idea being that when I talk about a numerical signature, this is something that is convenient to extract numerically, and that's going to be robust enough in finite size to give you a good indication of the nature of the ground state, but something that's not necessarily accessible in experiments. And numerics can also help you well, simulate experimental protocols in order to see what you should expect from your experiment and to guide you in the process of designing experimental protocols. So I will start with some physics about the fractional quantum Hall effect. So the Hall effect in general is a phenomenon that occurs when you have a magnetic field and you have a, well, you can measure a non-zero Hall conductivity. So a non-zero conductivity in the direction transverse to the applied current. At the quantum level, it means that we are going to restrict ourselves to two-dimensional systems. And if you diagonalize the Hamiltonian of an electron in a magnetic field and confined to dimensions, the answer you get from diagonalizing this single particle Hamiltonian is a spectrum which is made of these degenerate levels called Landau levels. So each level has a macroscopic degeneracy, which is equal to the number of flux quanta in the system. And you have a finite gap between each level, which is called the cyclotron energy. So from this picture, we can relatively intuitively understand where the integer quantum Hall effect comes from. So the integer quantum Hall effect corresponds to filling up an integer number of these Landau levels. So in a sense, it's a band insulator because the insulating character comes from the Pauli principle. Once you fill up the whole level, that's it, you have a gap. And that's going to result in a Hall conductivity, which is equal to the filling fraction times E squared over H. And the filling fraction here is just how much have I filled my Landau level. So filling fraction 1 means fully filled lowest Landau level. Filling fraction lower than 1 means partially filled lowest Landau level, and so on. So here, what I'm most interested in is the case where the lowest Landau level is fractionally filled. So I have mu, which is less than 1. And in this case, because you have this macroscopic degeneracy of the Landau level, if you didn't have any interaction, that would not lead to an incompressible phase. But due to strong interaction in the system, for some fractions, for some values of the filling fraction mu, you find that there's actually an incompressible, a gapped phase. At these particular fractions, the Hall conductivity sigma h is quantized. It quantized to mu times E squared over H. And the simplest example of such fraction is the Laughlin fraction. So in the introduction, I already mentioned the 1/3 Laughlin fraction, which was the first observed fraction in the fractional quantum Hall effect. It's actually a whole series of fractions at filling fraction 1 over m, where m is an integer. And in the solid state context, m is always odd. M is because it corresponds to fermions, but theoretically speaking, there's no problem to have a Laughlin state of bosons, and this is going to be for the case of when m is an even integer. So this fractional quantum Hall effect was the first experimental example of topological order. Since then, we also know that it's in principle possible to obtain phases that are in the same universality class as the fractional quantum Hall effect, but that do not require a large magnetic field. So this is obtained in what we call the fractional Chern insulator. So a Chern insulator is it's when you have a lattice system where the one band, or the lowest band, let's say, has a non-zero Chern number, meaning that when you fill it up, you'll obtain a non-zero quantized hole conductivity. And same as partially filling Landau level, you can partially fill this Chern band. And when you take into account strong interactions, you can obtain a fractional chain insulator, which is a fractional quantum Hall state without a magnetic field. And so here I'd like to, there are many examples of microscopic models that we have found numerically to host this fractional chain insulator as a ground state. And here I'd like to give you an example. So the it's based on the Harper-Hofstadter model. So if you first look, so in this box, I have the non-interacting parts of this Hamiltonian. So we have a square lattice with nearest neighbor hopping with amplitude t, and depending on which direction the particles are hopping, they either have an amplitude t or an amplitude t times some complex number exponential I phi. And due to this complex number, we can see that on every plaquette of the lattice, there is an enclosed flux equals to phi, meaning that if I have a particle that goes around one plaquette like this, its wave function is going to acquire a total phase of phi. Phi can in principle be any real number. In the case where phi is equal to pi over 2, it's quite convenient because it gives you a 4-band model with the 4 bands represented here. And the lowest band is going to be a Chern band, meaning it has a Chern number 1, which is going to be very practical in the context of fractional chain insulators. This model is one of many chain insulator models, but it's especially nice because it's been realized in the cold atom context, in the context of optical lattices. So that's just the single particle part. Now, adding strong interactions to this model, so I have the Hofstadter model on one side, and now I'm just adding bosonic Hubbard interactions. And I can wonder what is the ground state of that system. And numerical studies have shown that for filling fraction 1/2 of the lowest bands, filling fraction 1/2 of these red bands, the ground state is actually a bosonic fractional chain insulator, which is equivalent to the nu equals 1/2 low-flame fractional quantum Hall state. For some values of the flux, small values in particular. So now in the rest of the lecture, I'll talk a little bit about how do we know that? So how do we extract numerical data in order to make this type of conclusion? So first of all, a very general point about numerical signatures.
Just Cecile, we have one question from Adita, just concerning the e to the I phi phase in the hopping parameter.
Yes.
Asking if it's just for the model or if you have a more physical motivation why you define.
Yeah, so it's called a Peyer's phase factor. So if you write down if you write down a lattice in a magnetic field, it's the type of phases that you are going to write. So in a sense, this helps you capture the Arnold-Bohm phase that you would pick up from the magnetic field if you had one. Now, it depends what is the sense of the question. To have specifically those phases, the way that you place those phases, it's gauge dependent. So what's gauge independent is what is the flux on each plaquette. So you can place it however way you want as long as you have flux phi. Yeah, I think, does that answer the question?
Okay. Yes.
Okay, so now we can maybe start with some numerical signatures. Yeah, so a very general point about numerical signatures in general, typically we like to have bulk signatures, meaning that we like to have systems without edges because it tends to lower finite size effects. And this is especially true if you have a topological phase, because you have, for a topological phase, you expect gap length edge modes at the edge. So if you choose a geometry that doesn't have these edges, you don't have any edge modes. So you have a system that's fully gapped. So typically, this just makes things easier to have a system that's fully gapped, and it's easier to extract quantities that are universal and robust with system size. So what does that mean? In the context of exact generalization, this is often the torus geometry. And this is what I'm going to focus on this torus geometry for the rest of the lecture when in the context of exact generalization. The sphere is also very important, but really it's convenient only if you have a continuum system. So I want to be able to deal with lattice systems, and it's not easy to put a lattice on a sphere. So I'm just mentioning it for the sake of well, pedagogy, and because it's important from a historical point of view, because a lot of fractional economic whole exact generalization studies were first done on the sphere geometry. Now, there's a second advantage of not having any edges in your system, beyond the fact that you lower the finite size effects, is that you can use more special symmetries in principle. So on the torus, you have translation symmetry along the two axes of the torus. So that allows you, in the context of exact generalization, you can use these symmetries which commute with the Hamiltonian to block diagonalize the Hamiltonian, so that effectively you diagonalizing a Hamiltonian with a smaller dimension. And in the context of the energy, not having edges means an infinite cylinder. So you could also do a finite cylinder, but infinite cylinders are especially practical. And what does that mean to be infinite in this context? It means that you have a matrix product state which is translationally invariant. So what you do is you define a unit cell, which you are then going to repeat along the cylinder axis. Okay, so that settles the question on geometry. And now we also need to wonder about observables. Which observables are we going to measure or to calculate from our numerical data? So very often it's going to be spectroscopy, meaning some energy spectrum. For example, checking that you have a finite gap. I've said that topological order phases have a gap, so it's one of the few things, it's probably the first thing you should check to know if you have a topologically ordered phase. It could also be a degeneracy, so degeneracy of ground states or excitations. And as you'll see, when I say spectroscopy, sometimes it means energy spectrum, but it can also be entanglement spectrum, which is especially relevant in this context. And I'll talk more about this later. And then you have other observables that you could calculate if you have obtained the many body ground states. And for example, you could obtain the whole conductivity, which is quantized in these fractional quantum Hall, fractional chain insulator phases. So that's still very general. So now I'd like to focus for a while on exact generalization. And as I've said, for exact generalization, the most convenient when you have a lattice system is to use the torus geometry. So I'll talk now about exact generalization on the torus geometry. So the first thing that you can check, and maybe one of the easiest things to check along with the existence of a gap, is the degeneracy of the ground state. Indeed, generically, we know that for a system with topological order, there is the ground state is degenerate on the torus. Actually, the degeneracy of the ground state depends on the genus of the surface. So if you have a double torus, like a torus with two holes in it, it's going to be even larger. But here we just focus on the torus because that's what's accessible numerically. So the degeneracy on the torus is equal to the number of topological sectors. So what does that mean? If you have, I'm going to use again that example of the bosonic Loftin 1/2 states. There are two topological sectors in that case, which is the vacuum and the semyon. So really what you're doing when you're counting the number of topological sectors is you're counting the number of different anyons or different different excitations in the system. So you always have the vacuum, which is a boson charge 0. This one is always there no matter what, even if you don't have topological order. And then on top of that, for the 1/2 Loftin state, you have a semyon of charge E/2. Likewise, let's take another example. I could have used the Loftin 1/3 state, which is realized in the solid state context. Then I would have had the vacuum, one anyon of charge E/3 and one anyon of charge 2E/3. So that's 3 topological sectors. So I expect a ground state that is 3 times degenerate on the torus. And that's going to be different from one topological order to another. It's not unique in the sense there's not always a one-to-one correspondence. For example, a 3-fold degeneracy could correspond to 2 different types at least of topological order. But still, that's a very good first indication. So let's look at what it looks like in an actual energy spectrum. So I'm going to first use the continuum the problem of the functional common Hall effect in a continuum system. So here I'm considering bosons at a filling fraction 1/2. So I am at half filling of the lowest Landau level, and I have an interaction which is this delta interaction here projected onto the lowest Landau level. And so here I'm showing you the low energy spectrum for eight bosons in this system. And I've mentioned before that you want to use all the symmetries in your system when you're doing exact diagonalization so that you're block diagonalizing blocks that are small as possible. So here, the symmetry that I'm using is the translation, the center of mass translation along one direction of the torus. So this is why every eigenstate is labeled with this center of mass momentum. So here you see that you have a ground state at energy 0, and it takes exactly twice the generate. And then you have a gap delta to higher energy excitations. So this is one system size. We want to know how much this is representative of the fractional common Hall system in general. So we don't want to just see one size, we want to see a bunch of sizes and maybe see if we can extrapolate this quantity, the many-body gap, to the thermodynamic limits. And it turns out that the correlation length in the system is so small that even for relatively small sizes, the many-body gap starts to converge quite fast. So here I have represented the many-body gap, delta, as a function of 1/n, where n is the number of bosons. So if you want, the thermodynamic limit would be at 0 here. And we start with very small system of 4 particles here going up to 13 bosons for the largest system here. And then we can quite precisely extract an extrapolated version of the many-body gap. So maybe it's important to know that this is there's no prediction, there's no analytic prediction for what is the many-body gap in the fractional quantum Hall effect. So it's very so numerics are really necessary to obtain this value here. So this is okay. So this is my first case. Now I've mentioned lattice systems, so I wanted to also show you an example in not in the continuum, but for fractional chain insulator. Now I'm going to consider the same phase. So the question here is, I have a model. I'm going to take again the Hofstadter model that I presented in the introduction, and add some bosons, some interacting bosons to my model, and ask, is the ground state in the same universality class as the low-fin 1/2 fractional quantum Hall states? So I remind you the model here very clearly. This is the square lattice with nearest neighbor Hoping terms and fluxes. Yeah, just as a side note here, we often do some approximation, so you could simulate the whole model, but to reach larger sizes, very often you'll either say that you have small interactions, so the strength, the Hubbard U is small compared to the gap from the first band to the second band. Then you can project the interaction onto the lowest bands, which is exactly the same as the lowest Landau level projection that I showed in the previous slide. But you can also work in a different limit, which is the limit of very large Hubbard U. And then you can say that you have hardcore bosons, take U to infinity. And that will also restrict your Hilbert space a little bit, so that you have a slightly or a smaller Hilbert space dimension. And that helps you find the ground state for a few more system sizes. So here is the low energy spectrum in this case. So I have this model where I have a lattice that has 56 unit cells. So I have 56 states in the lowest band. No, sorry, that's 56. That's the total number of states. I only have 14 states in the lowest band, such that 7 bosons corresponds to a half filling of the lowest band. And I have represented this low energy spectrum as a function of lattice momentum. So here I'm using this linearized index here. It's just that I have a 2-dimensional lattice momentum, and I don't want to plot. I don't want to do a 2D plot, because I don't think it's very easy to see things on a 2D plot. So to have a 1D plot, I'm just doing this linearized index of kx plus nx ky. Here. So what we see now is that, again, we have 2 low energy states separated by a gap from higher energy excitations. But here you can see that there's a finite splitting of energy between the 2 low energy states. So I promised you a ground state degeneracy in the case of topological order, and in this case of 1/2 fractional chain insulator. But it's only an exact degeneracy in the thermodynamic limit. In finite size, unless you have a special symmetry, which is the case in the continuum, but not on the lattice, there is a finite degeneracy splitting, which we expect to exponentially go to 0 in the thermodynamic limit. So we want to check that what those 2 quantities, the many-body gap and the ground state degeneracy splitting, what do they do in the thermodynamic limit? So we can extract again those energies as a function of system size to see what we have. So similarly to my previous slides, I have a plot as a function of 1 over n, where n is the number of bosons. Here I'm working the hardcore boson limit, so I'm limited here to 8 bosons in a lattice of 64 sites in total. The red curve corresponds to the many-body gap. The blue curve corresponds to the jet generalist lifting. So the first thing I can say is that the generalist lifting it's quite small, but quite importantly, it's small compared to the gap. It's always small compared to the gap, but the system size is not large enough that you can see really convincingly that it goes to 0 in the thermodynamic limits. So, well, that's, we can't really do more at this stage. And the many-body gap has more finite size fluctuations. Still, it's quite convincing, or at least, yeah, I'm inclined to believe that it stays finite in the dynamic limits. Okay. Yeah, was there a
There's
question?
another question from Juan Diego. Why does the small delta seems actually to increase with system sizes?
Yeah, I think it's just not very universal. I think when you say that the small delta should be exponentially small, that's only true if you have a system that's large enough. And when you have these very small sizes, you can have all sorts of commensurability effects. So for example, I can have a system size where I'm expecting the 2 different ground states in different K sectors, in different momentum sectors. And then because I changed slightly the geometry, and now I'm expecting them in the same sector. And already that is going to have quite a lot of influence through level repulsion on the lifting of degeneracy. So I think it's just something that typically you don't pay too much attention to, as long as delta doesn't start to become the same order of magnitude as the many-body gap. I think it's just a finite size effect.
So what is the limitation to increase the system size?
Oh, it's hexagonalization. So for example, this point here for 8 particles, I think it's the dimension of the Hilbert space is around it's a few hundred million. And so the limitation typically is RAM. So if you want to store all the matrix elements of your Hamiltonian, then it's gonna be increasingly costly in terms of RAM. You don't have to do this, but if you don't store it, then you need to recalculate it at every length step. And typically in the system, there'll be hundreds of length steps. So at some point, it just becomes too costly. It just takes too much time to do the calculation.
I think we also have 2 more questions raised hands. So let's start with Artem, please.
Yes, I had a question, namely, maybe I don't quite get how you define the filling fraction 1/2 here, but I don't understand if you have 7 bosons but 56 sites, why does it give you a filling fraction of 1/2?
So that's it's a bit confusing when you write it like this, because so the filling fraction it's the difference between the filling fraction of the lowest bands and the filling fraction of the lattice. And in this context, we have the fractional column row context. We tend to define every filling fraction with respect to the lowest bands and not the lattice. So if you have several bands, that's not the same thing. And if I have when I have phi equals to pi over 2, I actually have 4 bands in the system. So maybe I can show you again the spectrum. Yeah, here. Those are the 4 bands. So there's a factor of 4 between the filling fraction of the lattice and the filling fraction of the lowest bands.
Okay.
Okay, and another question from Anton, please.
Yeah, thanks. So I figure your n stands for linear size in 1D, hence the total number 56. And you are saying that this finite number leads to some commensurability effects that drive delta larger. Hence my question, why do I try to, let's say, slightly alter an x and n y separately, so make the system non-square like a rectangle with like a close number of sides, total number of sides, but different geometry that will somehow alter the value of delta so that I could see it's like actual or like if you want geometry averaged behavior. Is this a good idea to do?
Yeah, absolutely. So this is there's one thing that you need to keep in mind is that what matters is you still want the smallest size. So you have those two directions. So let's say nx and ny, and you want both of them to be I don't know, a few times larger than the correlation length. So you can't have a system that's too anisotropic, right? Like you cannot do like a 1 by 56. That would be a 1D system.
No, that's true, but I mean like among.
No, I'm just bringing a small, the limit of this method. So, but you're absolutely right. It's always a good idea you can even do. Okay, that would be easier to draw, but you don't have to define the periodicity of your lattice along the same lines as your brother
That's
lattice.
exactly what I was about to propose, that you can actually try to arrange the translation in a diagonal fashion.
Absolutely. Yeah, it's a good idea, and this is definitely something that people do. Yes.
Okay.
Yeah, so then it's a good idea to try different geometries. Here I just I took a few points that were easy to find. I'm not sure it's going to be possible to do much better than this because I always aimed for the most isotropic system in this case. At the end of the day, I think it's just too small of a system size to see the exponential decay of delta. I think that's the short answer. But this technique that you're suggesting is definitely valid, and it's a great technique to use. Yes.
So if you I wonder whether you have any like actual data about it. Probably, I mean, how like scattered is the data for small delta if I try to arrange various like even exotic geometries with preserving the number of sides, just as we discussed this diagonal translation and etc. Have you tried like looking into that?
I could. Yeah, maybe later on I can send you some references. But I remember one case where I did a gap extrapolation. So it's not the small delta, it's the gap extrapolation. In one curve I have an aspect ratio for the torus that is as close to 1 as possible, and in another case I'm going closer to 1/2. For the aspect ratio. It's a little bit different, but it's not that different. I think the point is that as long as both your lengths, as long as the smallest cycle of the torus, let's say, is larger than a few times the correlation length, these considerations don't really matter. I mean, that's what you expect at some point. The system is large enough.
Yeah, quite expect.
But below that, there's a lot of non-universal things happening, and then you need to look at each system on a case-by-case basis.
Yeah,
I have a very general conclusion.
I see. Okay, there is a related question of whether any sort of analytical analysis is available for such type of behavior, because I figure there's a like at least a principal possibility to understand what are finite size corrections to delta in a certain well understood geometry. I don't know if this is the case, but probably they exist.
Not to my knowledge.
Okay, okay. Just whether I wondered whether you knew already. Yeah. Okay, I see. Thanks.
Okay. Was there any more question, or should I go on? No answer, so I'll just keep going. We've talked about the degeneracy of the ground states. Now I'd like to talk about the degeneracy of quasi-Hall excitations, because this is also something we can that can help us diagnose the nature of the ground state. So for many fractional quantum Hall states, and the Laughlin state is one of them, there is a general rule to predict the degeneracy of zero energy ground states once you have quasi-Halls added to your ground states. And this comes from the Haldane's fractional exclusion principle, which tells you that you can predict this degeneracy by counting the number of configurations with no more than k particles in R consecutive orbitals. So it's a little bit like a Pauli principle, where you can not have more than one fermion in one orbital, but here it's generalized to a few orbitals in a row. So it's maybe very abstract when I say it like this. So again, let's take the example of the bosonic Laughlin 1/2 states, which follows a generalized exclusion principle of 1, 2, no more than one boson in 2 consecutive orbitals. So here, orbitals are single particle states. They are Landau orbitals. It doesn't really matter. It's just a counting principle, so it doesn't really matter which basis you're using. So let's start with the ground states. If you want to write down the 2 boson ground state on the torus and you follow this rule, you will be able to write down 2 configurations, because you have a Filling fraction 2. So if you have 2 bosons, you have 4 orbitals. And for 2 bosons in 4 orbitals, I can write down 2 states, 1, 0, 1, 0, or 0, 1, 0, 1. That corresponds to the twofold degeneracy that we just talked about for the ground state. Now I'm adding one empty orbital, one more accessible state. I can add it at the end, but I actually have a few more configurations that will satisfy this no more than one boson in 2 consecutive orbitals. And I can write down 5 of those states. So I have, this predicts that I will have 5 degenerate states for the configuration for when I have 2 bosons and 5 orbitals, and I'm counting Laughlin quasi-Hall. A comment here, those configurations that I'm writing down, they are not at all eigenstates, of course. It's just a counting principle. And the reason it's not an eigenstate is that those configurations, they are product states, and fractional quantum Hall states, they're not product states. They are highly entangled states, so they consist of linear combinations of many such configurations and orders. So it's good to keep that in mind, but it's just a counting principle that helps you predict degeneracies. And those degeneracies, they depend on which kind of topological order you have. So it's a useful way to extract topological order from numerical data. Yes, I'm gonna, so I see that there's a raised hand. I'm happy to answer, but I'm gonna show an example which maybe is gonna make things clearer. So like I'm now talking about Again, the low-fin one-half states for bosons. So I'm considering a lattice with 12 unit cells. So I have 12 orbitals in the lowest bands, and I'm considering 3 bosons. So I would have the ground state for 6 bosons because that would be a filling fraction 1/2, 6/12. And I have removed 3 particles to obtain 3 bosons. So now I count the number of configurations of 3 particles in 12 boxes with no more than 1 particle in 2 consecutive boxes. And so you can write a little script to do this, and it will tell you that it's 112. So here is now the low energy spectrum corresponding to, again, I'm still using the same Hamiltonian of the Hofstadter model with Hubbard interactions, Hubbard-U interactions on sites. And what I obtain is a spectrum with a many-body gap here and a bunch of states below the gap. And if I count them, I can see that they are exactly 112, which is what was expected from the quantum principle. So it confirms the low-fin one-half nature of these ground states. Okay, so maybe I can answer the question now. Yes.
Anton, please, you can unmute.
Okay, yeah, thanks. I still don't get whether this counting principle actually provides you kind of a single particle like basis out of which the true eigenstate is made of. Whether this is just a way to figure out what is the true number of single particle states, or I can arrange a single particle basis in this principle. I mean, compose the true state.
Yeah, it's just a counting principle. Okay, so let's go back here. So here, let's take those even the first 2 lines of configuration. If let's say that I'm doing exact generalization of 2 bosons in 4 orbitals. So those could be like the 4 states in the lowest Landau level or the 4 states in my lowest band. I have a lattice system. Now I have written 2 states, but in practice for bosons there are a lot more states, right? I could have written 2, 0, 0, 0, or place this 2 anywhere I want, or I could have had 1, 1, 0, 0, and so on. So the actual low-fin states, the ground state, it's going to be a superposition of pretty much all of these configurations with different coefficients. All of them are going to be involved. Yet, as a counting principle, I can use this rule. So it seems like I'm taking this, out of the heart, and it's just magic. There is a rigorous proof in the main geometry based on counting Jack polynomials, which tells you why this rule works, basically. But for the purposes of numerics and of having a counting principle, you can just use it as a counting principle, basically.
I see. So this should be opposed to the counting principle for true fermions, where like eventually we get a proper basis for the single particle eigenstate as well, not just for the purpose of counting. I see. Okay. Right. Thanks.
Okay. Yes. So far I have so this is another way of extracting topological order from the energy spectrum. You could also do it from the entanglement spectrum. So I think some of you probably knew the entanglement spectrum before. Maybe you use it in your research, and in any case, you've you've used it in Marikaman's lecture, but here's your basic reminder. If you have a state, an anybody state psi, you can cut the system into two parts to obtain the reduced density matrix, which is a partial trace of the density matrix. And the entanglement spectrum in general is the spectrum of this reduced density matrix. Here, for the purpose of probing quasi-Hall excitations, it's very useful to do a cut that's not the typical cuts that maybe you used to, the left and right cuts, but a cut that's called a particle cut. So to do a particle entanglement spectrum, meaning that for my two subsystems, I'm going to consider NA particle in one and NB particle in the other, such that the total NA plus NB is the total number of, let's say, bosons in the system. So one way to think about it is when you do a Schmidt decomposition of your ground states, you do it on a basis involving states that have NA particle in one and NB in the other one. So if I take a system of 10 bosons, for example, maybe I have 6 bosons in the basis A and I have 4 bosons in the basis B. Or equivalently, it's the trace is done not just over a subsection, a physical subsection of the system. It's done over the whole geometry of the whole torus, for example, but on a subset of particle coordinates. And this particle entanglement spectrum is a way to extract the degeneracy of bulk quasi-holes from the ground states. So again, I'm going to show you a numerical example. So here I'm using the case of where I have 12 unit cells. So this is the same that I showed for the quasi-hole degeneracy using the energy spectrum. So I have 12 unit cells, 6 bosons. So this is the ground states because I have Binning fraction 1/2. But I take a subsection of the system with only 3 bosons to do my entanglement spectrum. And what I obtain is what I have here on the left. I have an entanglement spectrum which is gapped. So we talk about an entanglement gap and some states below this gap. And the number of states below this gap is exactly the same, is 112. So exactly the same as the number of states below the gap in the energy spectrum when I only had 3 bosons in the system and the same number, 12 unit cells. So I have, I have the same number of states below the gap. So it shows you that it's an extremely convenient way to extract the topological order from the ground states. So here, to do this entanglement spectrum, I didn't have to actually create any quasi-holes in the system. I only had to diagonalize the system once for the Binning fraction 1/2, and then calculate the entanglement spectrum for these ground states. So it's a very robust way of diagnosing the nature of the ground states because there's extremely very little chance that you would find this exact number, 112, just by chance. Okay, so this is the end of the exact generalization part. Now I'm gonna talk a bit about the MRG, but of course I can answer questions before I move on.
So there is a question in the chat.
Yes.
Could you please get back to the previous slide for a second?
This one?
Yeah, I think so.
Excuse me, I have a question as well.
Sure, yeah, go ahead.
Can you hear me?
Yes.
Okay. No, I was just wondering, I didn't get how these particles are ordered when you do the particle cut.
How they are Ordered?
I mean, you are saying that when you do the particle cut, you have to trace out, as you do in that formula,
Yeah.
some degrees
Yeah.
of freedom, no?
Yes.
How do
yes.
you choose them?
So they are still bosons. They're still undistinguishable. So maybe it's less confusing to think about it in the terms
Okay.
of the Schmidt decomposition, where you just write down your states as a sum of these products, where in the A states you only have states with a restricted number of bosons, but they're still indistinguishable.
No, okay. Okay, because I mean, when you have a boson state in general, it is characterized by all the occupation numbers of all the levels, no?
Yes.
I was wondering if one chooses some levels, for example, ordered by energy, until one reaches the number to trace out, or
no, you're gonna build the whole basis with that restricted number of bosons.
Okay.
And then you're gonna see how to write down your reduced density matrix in this basis.
Okay, I will try to think it over.
Okay.
We have another question, I think. Artem?
Yes, I had a question to the next slide, namely, now you speak about 12 unit cells. I guess this means 12 sites. No, but so how small is the correlation length that we're talking about here? It has to be like smaller than 2, or so it's like extremely
well,
small.
okay, so maybe we don't have 3 correlation lengths. Maybe we have like 1.5. Maybe we're not in a regime where we can say that okay, we don't have any finite size effects. We still do have some finite size effects.
I just mean it's like an extremely small correlation length that you will. I mean, that's a really special system, no?
Yeah.
You
So
will not
okay.
expect to get such a small correlation length in general. Or is it typical for these
Yeah. So
quantum
you should keep in mind that so I'm saying 12 unit cells, but the unit cell has several sites.
Okay.
So I think the data that I'm showing here is I actually took okay. So earlier I had this Hofstadter model where I had a unit cell with 4 sites. So you already have 4 times as many sites as unit cells. And here, I think for this data, I had something like 6 sites per unit cell. I think I did. So.
Great. So then how many physical sites is this in total?
So here this would be 72, but this is possible thanks to the projection of the interaction onto the lowest band. So in the end, all these bands, they get projected out so that it remains tractable with an excitabilization.
Okay, I see.
But yeah, otherwise, to answer the question about the correlation length, in these low flame 1.5 systems, the correlation length is roughly 1 or 1.2 magnetic length. So the magnetic length in these lattice systems, it's maybe it's like what is the linear size that you need to enclose a full flux quantum. So typically this will be 2 sites in my Hofstadter model, for example.
Okay, Anton, maybe ask your question.
Yeah, thank you. I kept staring at your previous slide, and actually I didn't manage to catch the main idea of this particle cut. I mean, what's the principal difference between this and just plain dividing of the system into 2 halves? Just simply Don't catch it apparently.
Yeah. So if you look at the integral here, I didn't explicitly write the window of integration. But if you had let's say the typical entanglement cut, which is a real space cut. Let's say I have a torus and I just cut it into two. I'm going to integrate in a window that goes from, let's say, coordinate 0 to coordinate L/2, when the torus is like the whole length is L. So I go from 0 to L/2, and then when I wonder, okay, which coordinates do I integrate over in this parenthesis here, I'm going to go from 1 to n.
Over
So
all of them.
I reverse the scheme and I go from 1 to nb instead of 1 to n, but the integral is over from 0 to L instead of 0 to L/2.
Oh, this. Okay, now I get it somehow. Okay, I see. Now it makes much more sense. Thank you.
I think there's no more questions, so
Okay.
I think you can go on.
Good. So now we can move on to a little bit of signatures on the infinity and the geometry with DMRG. So as we've said before, with hexagonalization, at some point, you're limited by the exponential growth of the dimension of the Hilbert space. So it's good to work in a smaller variational space, which DMRG does by using matrix product states. So it just works in this variational space with a smaller entanglement. And it's especially efficient for phases with topological order. So here that means working in the cylinder geometry, where with a quasi 1D, if you want a system where you have the cylinder perimeter, which is L, and you can have a very long cylinder. You can even have a translational invariant system along the cylinder axis, which gives you this infinite cylinder. Now, not going into the details of DMRG, but once you're in this geometry, how do you actually get the ground state degeneracy? Because typically, well, or generally, DMRG will give you the ground state, but it's not going to give you a whole spectrum. You can actually still get the ground state degeneracy. Okay, first of all, let me say, because you have an infinite cylinder, this is still the same genus as the torus, so you still expect, for example, the twofold degeneracy for this Laughlin 1/2 states. And these different states are accessible by inserting flux into the cylinder, which will actually permute the topological equal sectors. And if you want, you can think of it as this spectrum. So this is the spectrum you would get if you did it with hexagonalization, where you start at flux 0, and it takes the insertion of 2 full fluxes, 2 times 2 pi, to go back to the original situation. Your spectrum has a periodicity of 4 pi. This flux insertion can be done by adding a complex Robin amplitude at the boundary. So in the compact direction of the cylinder, the L direction, at one of the bounds, instead of having C dagger L C0, you want to add this flux here, which will effectively correspond to inserting the flux along the cylinder axis. This is also a way to compute the whole conductivity by measuring the flux adiabatically through the Laughlin argument, which tells you that introducing a flux phi in the cylinder results in a charge transfer Q, and that the whole conductivity sigma h is equal to the ratio between those two quantities. So now if you do it actually numerically, using this property of the whole conductivity. So again, I'm going to use that that Schmidt decomposition, but this time I'm using the typical cut. I have the left part of the cylinder and I have the right part of the cylinder, and I wrote down my my ground state as a Schmidt decomposition onto the left A and the right B part. And from this, I can calculate what is the charge which is transferred from left to right as I'm inserting flux in the cylinder. So this observable, the charge on the left, is actually equal to the Schmidt weight square times QL alpha, which where the QL alpha is the charge of the corresponding left eigenvector. Because charge is a conserved quantity in this system, each eigenvector has an associated charge. So here are some results which I extracted from this paper. So here you have the case of a trivial and an integer chain insulator. So in blue is a trivial case. So you see what is the charge on the left as a function of inserted flux. And in the trivial insulator, the charge on the left doesn't change as a function of flux. In the chain insulator, which is just a fully filled band, the charge on the left goes to 0 from -1 when you insert a flux 2π. And in the fractional chain insulator case, so here this was a churn band of filling fraction 1/3 with interactions, and here you see that to transfer a charge 1 from left to right, it takes an exertion of 6π flux, which tells you that the whole conductivity is equal to 1/3 times E squared over H. So it's a great way to verify the fractional quantization of the whole conductivity numerically using the energy. A second way, which is maybe even more powerful, is through the H spectrum. And for this, we're going to use the bulk H correspondence, which tells us that topological order in the bulk is accompanied by very specific gapless H states, and in particular, for fractional quantum Hall states, the H spectrum is described by a chiral conformal field theory. So again, taking the example of Laughlin 1/n, I could take 1/2, but it's actually generic. It doesn't matter on the denominator. Then the H spectrum is the spectrum of a U1 CFT, or if you prefer, a massless chiral boson. And it looks like this. So what you expect for the H spectrum is a series of states. So you expect a chirality, which I've represented by this black line here. And I'm representing the spectrum as a function of, for example, angular momentum. And what you expect here is a given degeneracy, 1, 1, then 2 states, 3 states, 5 states. And while the velocity itself is not something universal, not something that's going to help you diagnose which type of topological order you have, well, the degeneracy, those numbers here are universal, and actually they are tabulated in conformal field theory books. So the degeneracy that I've given here corresponds to the Laughlin states. So Laughlin 1/n, 1/2, 1/3, or whichever one you want. And if you went to a different fractional quantum Hall states, for example, non-abelian fraction, this would be a different series of states, a different series of degeneracies here. So this is again something that we can take advantage of when doing numerics to diagnose what is the nature of the ground state and find out what is the topological order in the ground state. And so you could in principle do that energetically. It's typically more convenient to do it through the entanglement spectrum. So that's what I'm going to show here. So I have again written my usual Schmidt decomposition. I'm doing the real states cut, the usual one, with states on the left and states on the right. And there's a general relationship between edge spectrum and entanglement spectrum, which was shown in these papers. It's actually also possible to extract the momentum along the cylinder perimeter for these Schmidt vectors, which helps you find the momentum resolved spectrum. And that can also be extracted in IE energy. So again, extracting this plot from this paper here, we see that it's possible to see the sequence of states as expected from conformal field theory, 1, 1, 2, 3, 5, and that would continue. So here, note that since we have a finite length along the cylinder perimeter, we only have a finite number of values of k. So here there were 1, 2, 3, 4, 5, 6 unit cells in total. So then the next stage we would expect to find again in the first, in a way the spectrum is folded, if you want, so that the next stage we'd expect to find them in the first momentum column. But here I think it's just mixed with the bulk states. So it's we cannot identify their content anymore. But it's clearly enough here. Again, this type of degeneracy is a very robust type of signature. So I think it's enough to have the first few ones here, the content for the first few ones to tell you what's going on. So it's a very powerful method for identifying chiral topological order. Yes, question.
Yes, I had a question on this picture. So, yes. I mean, I guess I understand where this comes from, but at least for the 5, it seems pretty arbitrary to choose these 5 states. No, I mean, the gaps in between these 5 states are larger than the one between the 5th and the 6th state. So in principle, of course, I can always cut 5 states off and say, this is them. So somehow, I don't know, is there some further analysis that tells me that, yes, these are the correct ones?
I think this, okay, so I think in that paper, they had this whole array of evidence. So they also had that whole conductivity that I showed in the previous slides, and maybe maybe some other things that I now forget about. And here, okay, I think it's a little bit harsh to say that you can always cut out 1, 2, 3, 5 states, because I've tried and sometimes it doesn't work, I can tell you. But I agree that if you had only that, maybe it would not be enough. But once you have all those signatures and they all point to the same direction, I find that quite convincing. I think in that paper they were also able to extract the entanglement entropy, which is a universal number. So typically this is not something that I find to be extremely convincing, because it's sometimes it oscillates a lot with system size before converging to a given value. I prefer to rely on countings. But yeah, I think it's a fair enough criticism.
Thanks.
All right, so now we're arriving at the end of this section on numerical signatures, or well, probably towards the end of the lecture itself. But I just wanted to give you a little bit of a summary of the techniques I presented. Some of them were on the torus based on exact generalization. So main signatures of topological order there are constant degeneracy and quasi-Hall degeneracy, which can be extracted either from the energy spectrum or from particle entanglement spectrum. And then we also saw some signatures of topological order for GMRG on the infinite cylinder, which were Hall conductivity to flux insertion, as well as edge spectrum from entanglement spectrum. Yeah, so of course, it's not a list that is completely exhaustive. It's a bit personal in a sense. I showed you the ones that I find to be quite convenient to extract, but also quite robust. Like for example, yeah, extracting a single number and trying to find whether it's quantized, for example, by calculating the Hall conductivity. That can be nice as a verification, but somehow, you know, when are you going to be satisfied if it's quantized to 10 to the -1, 10 to the -3? It's hard to tell. I find that if there's a gap and a degeneracy with a counting that's highly non-trivial, that's something that is quite robust. And, you know, in conjunction with different types of numerical evidence, you know, taken together, that can be quite convincing. And now a final comment on all of these methods is that they are, you know, I chose to present these methods because they are convenient numerically, but they may not, and typically they're not accessible experimentally. And the main reason is that they rely on geometry that are not realistic. So experimentally, you don't have a torus, you don't have cylinders. You typically cannot extract particle or any type of entanglement spectrum. So in the remaining time, I can either stop here actually and answer questions, or I can tell you a little bit about how to design and simulate protocols that can help you diagnose this phase experimentally, knowing that in the solid state context, you typically rely on the Hall conductivity, which will be quantized. So there's not much that numerics are really adding to that. But in other more, let's say, synthetic quantum matter systems, such as cold atoms, you don't have access to this quantity directly, at least not in the transport experiment. So you have to find other types of protocols, and numerics can help you do that. Yeah, so I'm gonna stop here, maybe start taking questions, and we'll see if we have time to talk at all about experimental signatures.
Very good. Thank you very much, Cecile. So we have time for questions, so please. May I ask one about the bosonic quantum Hall effect? Is there some quantum Monte Carlo scheme which can be also useful?
To find the ground state?
Well, I mean, because here's, well, you discuss ED, DMRG.
So okay, yeah. So I'm not so I think I'm aware of some Monte Carlo studies that, but they mostly use the model wave functions to calculate observables. For example, you know, one of the strengths of fractional quantum Hall is that you have model wave functions such as the Laughlin state or others, which which you can write down explicitly. And doing Monte Carlo with those wave functions can help you calculate densities or other observables because you know what is the wave function. Okay, but that's not. I don't think that's what your question was directly. But I'm not. I think you're always confronted with a sign problem if you try to do quantum Monte Carlo on these systems. Otherwise.
Okay. Okay. Mm-hmm. Okay, so do we have some questions? I don't see.
Just coming back, one question to your last slide. I think the slide before.
Yes.
Where you had in the plot, you have also the labeling 0, -1, 1, which actually seem to distinguish the states. So.
Yes. Yeah. Those correspond to because you have a charge label attached to every eigenstate. So it's true also for the Schmidt states. And yeah, I guess it's another argument actually in favor of this entanglement spectrum, which is that here those states here that you expect, which have the right sequence, are in the region of no additional charge, and the fact that you can yes, it's harder to distinguish the degeneracies based purely on the how much room there is or how much entanglement gap there is from one state to another. But since they have a different quantum number, you know that they don't belong to the same sequence, right? So it's not,
if you would look at the gap, which is just between 0 and 0, I think it's more convincing, at least for the first four
exactly.
states.
No, it's a very good point. Yes.
Okay.
May I ask a question?
Oh, sorry. Oh, yes, please. Yeah, please go ahead.
Hi, Cecile.
Hi.
So I wonder if the topological quantities that you are calculating, whether they are defined only for system, for a clean system, or in the presence of disorder, you can also define and calculate them.
Okay, so the whole conductivity, definitely. I think it's quite clear. So I mean, okay, so we're doing numerics. So in many cases, like all the exact normalization I showed, it would be very hard to do with disorder because we would have fewer symmetries. We wouldn't have translation symmetry. So the system sizes accessible, well, they would be much smaller. Okay, so that's the first question. But then, assuming that we can, yeah, I think that would still be robust, right? The spectroscopy, these energetic signatures, for example, from the I don't know, the quasi-Hall excitations, for example, they may be a little bit mixed up, right? They might be a little bit of degeneracy lifting, a little bit more degeneracy lifting, but I think it would be otherwise exactly the same. As it's just adding a perturbation. So as long as you're protected by a gap, I don't think disorder would change that story because we don't know this. I mean, we know this disorder would not localize those chiral 1D edges. So the topological order wouldn't change.
Okay, thank you.
Okay, very good. So if there are no more questions, I think we have to thank you, Cecile, once again.
Thank you, Cecile.
Thanks.
Thanks a lot.
And
Maybe
thank
we
you
can
all for your
stop the
attention.
recording.
Yeah.